Okay, for classwork 3.2, we are looking at sketching the graphs of logarithms. But before we sketch the graphs of logarithms, we need to remember how to graph their inverse partners, the exponential functions. So I'm going to start off with, if these are the exponents on 2 to the power of x, then what numbers am I getting for f of x? So 2 to the negative 2 power is 1 over 2 squared, 1/4. 2 to the negative 1 power is 1 over 2. 2 to the 0 power is 1. 2 to the 1 power is 2. And 2 squared is 4. And so what I want you to do is take that input, output, and swap for their inverse. If you remember back in the first unit that we did, we talked about inverses and did, when it's a table, you just swap the x and the y. So that means that when x is 1/4, f inverse is negative 2. When x is 1/2, f inverse is negative 1. And now I'm just going to write 0, 1, 2. There we go. Now, also, I want you to write the correct notation for the inverse of 2 to the x. And we learned that the inverse is log, and then whatever the base number is that you see for the exponential, that's the base on the logarithm, and it's a subscript. So it's a little bit smaller, a little bit lower. And then you go back up to where log was written and write the input variable in the same line as the log and the same size as the log. Again, that base 2 is subscript, and so it's a little bit lower and a little bit smaller. And then while we're at it, let's go ahead and make this table for 5 to the x. And the inverse function for 5 to the x would be log subscript 5 of x, so log base 5 of x. And then 5 to the negative 2 means 1 over 5 to the positive 2. 5 to the negative 1 is 1/5. 5 to the 0 is 1. 5 to the 1 is 5. And 5 squared is 25. And then do the inverse by swapping the x and y's. So then if you look at the directions, the next thing is to graph and label both of the functions on the same axes. Now, the thing that you have an advantage of here is you know what the graph of 2 to the x should look like, and you know what the graph of 5 to the x should look like. So I'm going to start with 2 to the x. And actually, I'm going to do this. While I draw, I'm going to have this up so I can show a little bit better. There we go. I am going to plot the points for 2 to the x in blue. So I have the point negative 2, 1/4 is, say, about here. And then negative 1, 1/2, 0, 1, 1, 2, and 2, 4. I want you to think about what the exponential growth graph looks like and the fact that it's asymptoting over here. So it looks a little bit like that. And the next thing we're going to do is we are going to plot points on the log table. And so I'm going to change my color to red as I do everything for the log function. I'm going to plot the point x is 1/4, f inverse is -2. 1/4, -2, about there. And then when x is 1/2, the y is -1. When x is 1, the y value is 0. When x is 2, the y value is 1. When x is 4, the y value is 2. And now I want you to think about what the graph of this inverse function should look like. And I want to point out to you over here that on the left end of the graph, you have your function asymptoting. So that means the inverse function is going to asymptote also. And then take a moment to think about the fact that over here, you're dealing with negative x values. They are very positive small y values, or they are giving you very positive small y values. Now you're going to switch that. So let me again say when you have very negative x. So I'm looking at this shows very negative x's are giving positive very small y values. The inverse is going to switch that around. So where you have very negative y values, that is going to give you small positive x values. Do you think you see what's going on with the graph based on what I just said? Let me also say that on the graph of e to the x, or sorry, not e to the x, scratch that completely. You don't know about that yet. On the graph of 2 to the x, you have, this is giving you an asymptote. Let me just point this out. Asymptote. And it is a horizontal asymptote. If x and y just completely swap, then that means you're going to have an asymptote here that is vertical. So there's an understood dashed line for the y-axis down here. And that means that the graph stays, it's very important, it stays to the right of the y-axis, but it is asymptoting down. And now something to think about. You've been told that exponential growth is pretty insane. It's very quick growth. And that's actually why there is concern for human population, because if humans breed without any control, we will continue this exponential growth, which will become a problem. And then it won't be exponential growth because too many people will have to die. We don't want to live in that world. So there is concern because exponential growth is very fast. So with that in mind, I want you to think, however fast exponential growth is, a logarithm has to compensate in a way for that incredulous growth and grow really, really slowly. It does grow, but I think of a logarithm as a snail on the back of a turtle. I don't know if you guys have seen, there's this cute little comic with a turtle and a snail's on top of the turtle going, wee! Anyway, that's the way a logarithm grows. It grows so slowly. But then just when you think it's growing too slowly to even bother watching, it slows down even more. So it's a very, very slow growing function. And actually, you guys might know this already, our earthquake scale and a lot of actual scales that we use for earth, what am I trying to say? I'm probably going to use the wrong word, so I won't. Earthquakes, the Richter scale. Do you guys know that when you go from a 4.0 to a 5.0, that is increasing its intensity by 10 times? And to go from a 5.0 to a 6.0, the intensity is increasing 10 times what it was. So basically, however familiar you are with earthquake numbers, if you're getting a 6 point, from my viewpoint of living in California my whole life, a 6 point or higher, if it's nearby, I'm going to feel it. But if it hits 7, it's not good. If it hits 8, there will most likely be a death toll and there's going to be some serious destruction. But have you heard about earthquakes that are 9 and higher? They are freakishly bad. And apparently there has been record of that up in Alaska. I don't remember the year. I just remember that I learned that at some point, I think a couple decades ago. What? Yeah. Oh, you know which one I'm talking about then. Or maybe it's a more, but yeah, those 9.0s, those are bad. Because if you think that 8 is serious destruction, 9 means 10 times more intense. So when you're looking at a scale, a Richter scale number, going from an earthquake level 4 to level 5, wait, did I just say that wrong? I'm sorry, I just said that wrong. Hello. I'm trying to find. Because the logarithm is looked at as the intensity is like the input, and the number that we are getting is the output for the scale of that. But this isn't the correct one anyway because it's base 2. But I just wanted to kind of put some context into that. Okay, now let's take a look at graphing the logarithm with base 5. And we can start by graphing the exponential function. So I'm going to put that in blue and plot those points. You may have already plotted these points. I can't plot this point, which means I'm not going to be able to plot this point over here as well. And let's see. -1 is 1/5. And I'm going to have a really hard time plotting the -2. It is just so ridiculously close. So you want to realize that this larger base, the 5 being larger than the 2, that asymptote's much faster. You know what? I know what my problem is. I don't have my glove on. Okay. do you see that this exponential graph is steeper than what you see with 2 to the x? Now, the good news for you is I'm not going to expect you to know the steepness of a 2 to the x versus a 5 to the x. What I do expect is that you can plot 2 points to be able to show the difference between the two. Same with logarithms, is plot 2 points. So I'm now going to move over to my red pen. And we are going to plot the point 1, 0 and 1, 5. And I want to tell you that, I'm sorry, I just read that wrong. 5, 1, I can do this. All right. I want you to know that these 2 points that I just plotted, those are the easiest to plot points for any base of your logarithm that you are given. And I'm going to emphasize to you that the easiest ones to plot are the ones where the y values of your logarithm are 0 and 1, when the y values are that. Because when the y value is 0, it is always going to be, that's where the x coordinate is 1 for a logarithm. And on a logarithm, when you're getting out a 1, that's because you're putting in the number of the base. So I want to highlight that over here as well. For the y value of 0 and the y value of 1, we were able to plot an x-intercept of 1, and then the base number 2 was the input that gave a 1. And over here, I'll repeat, when y is 0, x is 1 for every logarithm. When I get out a 1, I put the number of the base in, and that was 5, and so I got that point. Those are the 2 points I expect you to plot. After that, you just need to show me that you understand the essential behavior of it asymptotes and then grows slowly in this direction. Okay, then for domain and range, the exponential functions, their domains are negative infinity to positive infinity. And that's something you should remember from the previous unit. And the range is only positive y values. So the range is 0 to infinity when you are dealing with exponential. Now, when you turn to the logarithms, those are the inverse functions, f inverse and h inverse. They swap domain and range because they are swapping x and y. The most important thing that you need to see here is that the domain of your logarithms are positive numbers only. You can't put negative numbers inside a logarithm. I just wrote that wrong. There we go. You can't put negative numbers in a logarithm, and you can't put 0 itself into the logarithm, thus the round bracket. But the range, you can get anything out of a logarithm. If you just have a general logarithm function. Now, asymptotes. When you're dealing with exponential graphs, the asymptotes are horizontal lines at 0. And if x's and y's are swapped, that means that the asymptotes on the logarithms are x equals 0. When you look at your exponential graphs have y-intercepts, but they do not have x-intercepts. So the intercept of the parent graph is 0, 1 when you're dealing with exponential. But then for the logarithms, they are taking that xy coordinate and reversing their order. So we can remember from the exponential functions that their parent graph always goes through the y-intercept of 1. That means that their inverse partner goes through an x-intercept of 1. And so, wait, did I just read? No, hold on. I'm trying to think because I'm rewriting. Oh, dear. Just give me a second. I'm still like, I think I needed a break between period 1 and 2 to reestablish what I was thinking about. Okay, anyway, so there we go. It swaps the x and the y to get 1, 0, and you now have an x-intercept. So let me emphasize this is, come on, pen. This is an x-intercept. When you're dealing with the logarithms, they have the same x-intercept that the exponential had as a y-intercept. Okay. And that is my 10-minute alarm. We have 10 minutes left. And so the next thing I'm going to do is everything I've just been saying, I'm just going to point out in general. But for starters, I do have a little bit in here that I want to emphasize. Hold it. There we go. Now, today we are working on logarithm graphs where the base that we get is only a number that is greater than 1. If you remember with exponential graphs, you got a different looking graph when it was a decay model. So if the base of your logarithm is greater than 1, then you are dealing with the reflection over y equals x of your exponential growth graph. Now, do you remember what I just said about the domain of a logarithm? You can't put, if b represents a positive number, negative b is a negative number. You're going to get undefined for any negative number you try to plug into the x in a logarithm. And if you try to plug 0 in, you're still going to get undefined. You have to put a positive number in. And you need to be very familiar with the following 2 points. If x is 1, you're getting out an answer of 0. And it helps to keep in mind that when you are writing these logarithms, the answer is the exponent you would be putting on that base that would give you an answer that is here. So if x is 1, then b to what power is giving you 1, and that's always going to be 0. And then if you are looking at putting in the actual base of that logarithm, the answer to that is b to what power is equal to b. And let me make sure that you see who's who. And so I'm going to get an answer of b if my exponent on b is 1. And so that's what I meant by the 2 points that are going to be easiest for you to plot are going to be the ones where the y values are 0 and 1. And so what I'm going to have you draw here is you're going to draw a point here at 1. And then I want you to, anywhere on the positive y-axis, put a b. Pick a b. Or, I'm sorry, hold on. Oh, I'm doing it again. I'm like scrambled right now. And I just needed a time to pause in between classes. But here we go. So put a value of a 1 on the y-axis. And then I want you to decide what your b is. It's up to you. Pick anything larger than 1 to be your b and just write down a b. So maybe, let's see, maybe I'll call this b just to make it random. So I'm always going to expect you to plot the point 1, 0 and b 1, and the base is going to be some number larger than 1. And then draw. The important features are domain is only positive numbers. And this is no matter what base you are working with, provided the base is a number larger than 1. The range is all real numbers, negative infinity to positive infinity. And I want you to understand that as x approaches infinity, so as your input goes further out, this is slowing down dramatically. Just like when the intensity of an earthquake increases, the answer we give for its number on the Richter scale, it's got to go much further in intensity to go up a level. And so the growth is that it continues to get bigger. It does get larger, but it slows down. And it slows down forever. It just continues growing slower and growing slower and growing slower. And then the vertical asymptote is the equation x equals 0. That's for the parent graph. Now, what I'm going to want you to do is be able to start with a parent graph, deal with multiplication, and then bring in the addition subtraction. So, and let me double check my time. I have 3 minutes. Here we go. Log base 3 has x-intercept of 1. And when y is 1, we had to put the base in to get out the y value of 1, and then asymptotes. We're going to follow these particular 2 points as we go from the stretching and then to the movement. If I'm multiplying outside the function, then that stretches the y. the y values are multiplied by 2. The only y values I expect you to come in with are 0 and 1. So 0 times 2 stays at y value 0. Now your base number is 3. The y value is originally 1, but when I multiply 1 by 2, it goes up to 2. And then draw. And by plotting those points, it'll show a bit of that vertical stretch, but I don't expect perfection, just a basic shape out of that. Now, I still have the multiplication by 2 with the same log base 3. So now you're going to take the graph that you have in part B, and you're going to move it. The arithmetic outside the function moves up and down, and you go in the direction it says. And inside the function, it moves x and the opposite direction, so left 5. Realize by moving left 5, that's going to move this vertical asymptote. It's best for you, for your own sake of getting a good drawing, is to go over to -5 for the x coordinate and draw a dashed vertical line. That will help you to see not to graph anywhere to the left of it. Then I'm going to move 1 point at a time. So I have my original point of 1, 0 is going to move left 5 up 1. So left 5 up 1, and there's where it moved to. And then I'm going to take the point that is here, and that is 3, 2. And I'm going to also move that up 1 and left 5. So left 5 and up 1. And then draw. All right, and it's 10:50, time for you to go. So I hope you enjoyed that, and I'll see you tomorrow.